We're looking at the function f of x equals sine x over x. This is an interesting little function. It's useful. It pops up, especially when we're talking about limits. So it's a good idea to just remember, as we've seen before, that the limit as x approaches 0 of this function is 1. And we can get that by looking at the graph. It's also possible to do it using the squeeze theorem. But this opens the door, along with those limit properties, to knowing a whole bunch of other limits that are related to this one. It's not just sine x over x, it's sine whatever over the same thing. As x approaches 0, the limit is 1. So, for example, I could say the limit as x goes to 0 of sine 12t over 12t. Well, those are the same. So that limit is 1. The limit as, probably not x goes to 0 if I'm going to use t. That should be as t goes to 0. The limit of, let's see, we'll have x go to 0 of sine, I don't know, let's do x to the 7th over x to the 7th. Still 1. Well, then the question comes up, what if they don't match? Like, what if I have the limit as k goes to 0, I'm going to try to make my variables match this time, of sine k over 2k. Well, if it was sine k over k, I'd know what to do with that. That limit would be 1. But I have this extra 2. Use algebra. We can separate this fraction at the, into two pieces here. So we have the limit as k approaches 0 of, I'm going to bring this 2 out. That's 1/2 because it's on the bottom. And then left on the top is sine k, or sec, over k. But I know that this limit is 1. That's a constant, so its limit is itself. So this limit is 1/2 times the limit 1, which is 1/2. Coincidence? I don't think so. We had a 2 down here, and now instead of the limit being 1, it's 1/2. What if I have something like the limit as, q goes to 0 of sine, what if the 2 is up here instead of on the bottom? 2q over q. We can't do exactly the same thing that we did up here, and I'm going to look at this and say, oh, I really wish there was a 2 down here on the bottom. Well, guess what I'm going to do? I'm going to put a q down here on the bottom. So I have sine, not the sine, that's okay, sine of 2q over 2q, but now I've just changed the function, so I have to change it back because we can't change to a different function midstream here. Well, in order to make this back into the original function, I can multiply it by 2, or 2 over 1 if you want. Now when I multiply sine 2q over 2q times 2, my 2's divide away, and that really is, all of this put together really is the same thing that I started with. But I know that the limit as q approaches 0 of sine 2q over 2q is 1. The limit as q approaches 0 of a constant is itself. So for this limit here, I have 1 times 2 is 2. Well, if we put all that together, we put these last two things together, if I want to do the limit as, I'm going to go back to x approaches 0 of, say, sine 3x over 4x. I'm going to slide up so you can still see this. Then we saw from the one immediately above that 3 is going to become part of the limit. And the 4 is also, the 3 is on the top, the 4 is on the bottom. So without further, I mean, I could go through both of these processes with this, but I don't really want to. We're just going to recognize from those last two examples that my limit here is 3/4 without doing anything else. In general, limits like this, limit as x approaches 0 of sine of something times x over something else times x. Take the a from the top and the b from the bottom. Generally, that's how those work. Slide again. Think about this for a second. I promise somebody's going to do this to you someday if they haven't already. Don't assume that because it says sine x over x, the limit is automatically 1. Take a look over here. I'm not approaching 0 anymore. I'm approaching infinity. As x gets larger and larger and larger, sine of x is bouncing back and forth between +1 and -1. As x gets larger and larger, I have 1 over something really big, which is going to 0, which trumps the numerator. So watch out for that. All of this applies as long as we're looking at a limit as x approaches 0.